So today we're going to talk about eccentricity and conic sections. So we're going to define our conic sections. Instead of using two foci in certain circumstances, we're going to define all of them with one focus and one directrix, just like we did with parabolas. And then we're going to say that if Q is some point on the locus definition, and if F is the focus, and N is that point on the directrix that's nearest to Q, just like we did when we were defining a parabola, then the eccentricity is the ratio between Q to F and Q to N. So Q to F is the distance from any point on to the focus, and then Qn is the distance from that point to the directrix. And that ratio is going to be called eccentricity. So in the scenario where we had a parabola, we actually were using eccentricity was equal to 1. So in other words, 1 was equal to Qf over Qn. And that means, of course, when I multiply both sides by Qn, that Qf and Qn are equal, which was exactly our locus definition of a parabola. So if any of these points along the line here, or not, sorry, along the parabola here are the point Q, for example, this one right here is a possible point Q, or this one over here is a possible point Q, then the distance from that point to the focus or that point to the directrix is the same. Or in other words, the ratio of those distances is equal to 1. So that happens at the vertex, that happens at these 2 points, etc. There's lots of points. All of the points along the parabola satisfy this ratio is equal to 1. And again, the eccentricity, which we use the letter E to describe as eccentricity, is equal to 1. Now, there's an interesting thing that happens with a parabola, and that is that you can use what are called parabolic mirrors, which are mirrors shaped in the shape of a parabola. Actually, they're three-dimensional, so they're paraboloids, but that's not important for the discussion right now. And what's special about a parabolic mirror is that if you have light coming in straight into the parabola like this, that all of those beams of light will be reflected onto the focus. So that really is the focus, if you think about the idea of focusing light of this parabolic mirror. So all the light coming in will always reflect into the focus. So if you want to collect a lot of light on one spot on that, when you're collecting information like a telescope or something like that, then having the light reflect all onto the focus means you can get all the light coming in, all hitting that one spot, and that's where you would do your light collection. So this is true about telescopes. You can also look at satellite dishes. They'll have this parabolic shape, and then there'll be a spot sort of inside there where the light is being collected, or the radio waves, or whatever it is that you're trying to collect on that focus. Okay, so let's take a look at an ellipse. So for an ellipse, the eccentricity is going to be a number between 0 and 1. So again, if I'm using E for eccentricity, that's a value between 0 and 1. So for purposes of explaining how this works, I'm going to let the eccentricity be a half. And remember, eccentricity is the distance Qf over the distance Qn, that ratio. So 1/2 equals Qf over Qn. If I cross multiply to rearrange this, I end up with Qn is equal to 2 times Qf. In other words, any point Q, the distance to the directrix is going to be double the distance to the focus. So for example, if I've got my focus here and my directrix here, this is an example of one of those points Q, that's one of the vertices, and you can see the distance from that point to the directrix is double the distance from that point to the focus. So that's one of those vertices, one of the points that satisfy Qn is twice as long as Qf. And then the other vertex on the other side over here is another one of those, where the distance to the directrix is exactly double the distance to the focus. So you get one vertex on the in between the focus and the directrix where it's twice as far away from the directrix as it is from the focus, and you get another vertex further out than the focus so that it's twice as far to directrix as it is to the focus. And of course, all the other points on the ellipse will also satisfy this relationship. So that's how you can get an ellipse with a directrix and a focus using this eccentricity ratio, in this case again between 0 and 1. Now, one interesting thing about ellipses that has to do with sort of real life is that the orbit of, let's say, a planet around the sun, or the moon around the earth, etc., is an ellipse. Now, that's not entirely true because planets interact with each other, and therefore it's going to be a little bit wobbly. But if there was just one sun and one planet, you would get an elliptical orbit. And the interesting thing about it is the sun would be at the focus, and then of course the path of the planet would follow the ellipse. So this sort of scenario here describes the orbit of a planet around the sun, or of a moon around a planet, etc. So now let's consider a hyperbola. For a hyperbola, again using the directrix and focus, we use an eccentricity that's larger than 1. So for the example that I've drawn here, I'm using eccentricity of 2. So again, remember eccentricity, you use the variable e, and it's the ratio of the distance from a point to the focus over the distance from the point to the directrix. So again, if I take this equation here and I multiply both sides by qn, then I'm saying 2 times qn is equal to qf. In other words, the distance from the point to the focus is now double the distance from that point to the directrix. So the focus is farther away from the point, and the directrix is closer to that point. Again, I'm using 2 as an example, but any value greater than 1 would satisfy this and get a hyperbola. So in this particular scenario, if I take, let's say, this vertex, then this vertex would be one of the points Q, and you can see how the distance from the vertex to the directrix is shorter, and the distance from the vertex to the focus is longer. So the distance from the vertex to the focus is double, in this case, the distance between the vertex and the directrix. Of course, the vertex now is in between the directrix and the focus for that particular one, but it's not halfway in between like it would be for a parabola. It's closer to the directrix this time. In fact, exactly half as far as it was from the focus. Now, this other vertex on the other side of the directrix also has that property where the distance from that point Q to the directrix is exactly half of the distance from that point Q to the focus, or in other words, the distance from Q to F is double the distance from Q to the directrix. And again, any point on either half of the hyperbola will satisfy that rule about the distance from that point to the focus is twice as far as the distance from that point to the directrix. Now, there are also hyperbolic mirrors that are also used in things like telescopes and things like that, but I'm not going to go into too much detail. Obviously, it would only be a half of a hyperbola, not a complete hyperbola, because you wouldn't want both sides occurring. All right, so a circle, you can actually do it using a focus and a directrix, but it would require the directrix to be infinitely far away, and so I couldn't draw that diagram. But it's much easier to define a circle simply as the locus of all points that are equidistant from the center, of course, all points on a plane. So I'm going to stick with that, but technically you can do it with the directrix that's infinitely far away, and then the focus becomes the center of the circle. So it turns out that eccentricity can also be described in a different way, which is where the name conic sections comes in. So we're going to use a cone. Now in math, a cone is actually what you would maybe consider a double cone, where you have, so I'm just going to pick one of these diagrams. So you have the upper half of the cone, what you'd think of as a cone, which kind of looks like an ice cream cone. And then you have the lower half of the cone, which is perfectly symmetrical on the other side, which kind of looks like a birthday hat. So the ice cream cone and the birthday hat combination in math is considered a single cone. Now, conic sections are created when you come in with a knife and you slice through this cone, and then you see what the shape of the slice is that you're left over, the cross section. So in order to get an eccentricity is related to the angle compared to that cone, the angle that you come in with your slice. So, for example, if this cone is perfectly vertical, and of course there's the middle of the cone, then if you come in with a slice that's horizontal, so the angle compared to the x-axis is 0, then you get a circle when you make that cut. So with an eccentricity of 0, you get your circle. Now, when you start angling this knife a little bit to the point where it's somewhere between the horizontal and something less than whatever the angle for the edge of the cone is. So for example, if you come in at this angle, then what happens is, so that's an eccentricity somewhere between 0, which would be the horizontal, and 1, which would be parallel to that edge of the cone. So if you angle it that way, then you end up with an ellipse. It basically stretches out that circle a little bit to generate an ellipse. And the more your eccentricity, the larger that angle is, the more extended that stretching is. So you get a longer and longer major axis on your ellipse. Then, if you bring the knife in perfectly parallel to one of the edges of the cone, one of that sort of side view of the cone, and you bring your knife in, as long as you don't cross through the very center, but you come in and you cut 1/2 of the cone, that actually ends up giving you your parabola. So that's the eccentricity of 1. Eccentricity 1 means perfectly parallel to one of the edges of the cone. So that ends up giving you your cross section, which is going to be your parabola. And then finally, when you bring your knife in at an angle that's even steeper than the edge, so in this case it was straight up and down, then you're going to cut both the top and the bottom halves of the cone, and that will give you your hyperbola. And again, that's an eccentricity of bigger than 1. So your angle is steeper than the angle for the edge of the cone that generated the parabola. Now, this actually allows you to get another result, which are considered degenerate conics. So those are technically slices of this cone that don't end up giving you the circle, ellipse, hyperbola, or parabola scenario. So for example, if I bring my knife in and I slice it exactly through that point at the point where the top and the bottom of the cone intersect, I'm going to get a point, not a circle or an ellipse or anything like that. I'll just get a single point. So a single point is a degenerate conic. It's a very simplified version of a conic section. Also, if I bring my knife in and I slice it exactly this way, exactly along one of the edges, I could get a single line from that. Or if I brought my knife in and I sliced it vertically, kind of like the hyperbola one where I was going up and down, except that I made sure that the knife cut through the point that they meet with each other, that corner, then what you would end up with, you'd end up with 2 lines, one line like this and one line like that intersect at that center. So those are the degenerate conics that you could end up with. Either just the dot, because you just cut it this way and you only intersected the cone at the corner, or a single line by cutting it just barely at the very edge there, or 2 lines where if you cut it straight up and down, or even at an angle, but making sure that it intersects at that point, then you end up with just the 2 lines, for example, represented by this line and this line, if you brought it in and sliced it in the right way. So those are some degenerate conics. And if you were to set up, if you were to start with an equation that you think, oh, maybe this is going to be an ellipse, but then it worked out that you couldn't actually make one side equal to 1 because it turned out to equal 0, then that is a degenerate conic. That in that case would be a point. Or if you had a hyperbola where you're like, oh, okay, this kind of looks like a hyperbola equation, but then you tried to make it equal to 1 and you couldn't because one side was equal to 0, then you probably had the 2 intersecting lines scenario, which is a degenerate conic as well. And that is the end of the video.